We want to look at how to graph some different variations of the sine graph. And so to do that, I want to reinforce a couple ideas that we've alluded to previously. First of all, notice I just drove. I created the basic y equals sine graph. It's what we're familiar with. And we notice that it basically follows a nice smooth curve, ideally, all the way over the course of its entire cycle. The sine graph has a period of 2 pi. Now that's useful for us because that tells us the key points in between. Notice that I have a maximum, I have a 0, a maximum, a 0, a minimum, and a 0. Basically divides this graph into 4 chunks, where after the first quarter of the graph, I have a maximum. Halfway, I'm back at 0. 3/4 of the way, I'm at a minimum. And then 4/4 of the way, I'm back to 0 again. So when we look at things, we want to determine what is the chunks of our period. And how we do that is notice that our entire period is 2 pi. So I'll take the period and divide it by 4, because that gives me each of the 4 places where something good will happen at. And this reduces down to pi halves. So what that explains to me is that every pi halves, I'm going to get a maximum, a minimum, or a 0. Now, this is also useful because not all graphs that we're going to do have a period of 2 pi. Maybe the period will be just pi. And then therefore, each of our maximum minimums won't occur at a pi half spacing, but some other type of a spacing. So we want to learn how to determine its period, and the usefulness of that is to help us determine its maximums and minimums. Now, when we're going to graph these things, there's 5 points we want to look at. Again, I mentioned those. There's usually 3 zeros, a maximum, and a minimum. Another thing that we want to explore, and I'll do it by way of example, imagine that I have a graph that's the y equals maybe like 2 sine of x, where I have a value in front of the sine, like a coefficient, and we call that the amplitude. And what amplitude means is that in this particular case, it's 2. At every point along this graph, my values can be twice as much. So for example, at the point pi halves, I have a value here of 1. Well, it's going to take that value and stretch it or multiply it by a factor of 2. So I have a point up there. And over here on the minimum, I'll have a minimum point that's a factor of 2 down. And then obviously at 0 and 0, those get stretched out to exactly the same. So the amplitude then, this number, will create a graph that will look such like this. If I can graph it a little bit better there, or if I can graph it with a smooth hand. So it takes a normal graph and the amplitude will stretch every point by a factor of that amplitude. In this case, it is 2. So we're going to look through some different situations here, and I'll give you a little bit of a plan of how do we graph variations of sine x. As we learn to graph some variations of the sine curve, let's develop a little bit of a process that will help us do such. I have listed generally the 5 steps that we'll do as we explore some different functions. The first one is about the amplitude and the period. So notice here that I have my basic y equals sine graph that we discovered before. Notice also too in this graph, which I think you've noticed, is that there are 5 key points. And you notice I have them listed on the circle. These points represent at the points x equals 0, x equals pi halves, x equals pi, x equals 3 halves pi, and x equals 2 pi. Those are the 5 key points, because at each one of those points, we either have the graph crossing the x-axis, or we have a maximum, or we have a minimum. So those 5 points divide our graph up into 4 segments. There's one segment, a second segment, a third segment, and the fourth segment. Now that's useful information to help us determine the period of a particular function. Now what a period means is that you take one full cycle. In this case, I have a cycle that takes 2 pi to complete. At 0, I don't get back to that same type of 0 until I get to 2 pi. And over that 2 pi, I've gone through 4 different sections. So I'm going to take the period divided by 4, which will produce pi over half in this particular case. And that tells me then that I have a key point every pi halves along the graph. So at pi halves, I have a maximum. Another pi halves, it crosses the x-axis. Another pi halves, I have a minimum. And another pi half, it crosses the x-axis. So we're graphing different versions of the sine function or other functions. We want to take its period and then break it on up such that we get our 5 key points. So step number 1, it's about finding the period of the graph. In this case, the breakdown of the period, which is pi halves. The second type of thing that we want to explore is this idea of amplitude. So let's imagine then that I'm going to look at this graph and I'm going to look at another one that's maybe y equals 2 times the sine of x. So what do you imagine is going to happen with that? You're right. That's going to take every point on my graph and multiply it by a factor of 2. So this first point that's at 0, if I multiply that 0 by a factor of 2, I still have a 0. This next point at pi halves has a value of 1. If I multiply that point by a factor of 2, I'm at 2. Likewise, if I continue on, every point on this graph gets stretched by a factor of 2. So this point, that might be around 1/2, that's going to get stretched up to 1. From there, what I can do then is draw a nice smooth curve that connects those points. So these 5 steps I've kind of done. So let's go back and talk about exactly what I've done in this process. First of all, I've identified the amplitude. In y equals sine of x, the amplitude is 1. In y equals 2 sine of x, the amplitude is 2. And the amplitude is a stretching or a shrinking component. I identified the period. Sine graph, the period is 2 pi. From there, I divide 2 pi up into 4 chunks because that develops each of my 5 points or my 5 locations starting with 0. Now, not every function we're going to deal with has a period of 2 pi. Some of them may be different, and because of that, that will determine our key points. The second thing that we've done is use x values at those 5 key points. 0, pi halves, pi, 3 halves, and 2 pi. I identified those 5 key points. Step 3, I took those 5 key points, then I evaluated them based on our function. So the sine of 0 is 0. The sine of pi halves is 1. The sine of pi is 0. The sine of 3 halves pi is -1. And the sine of 2 pi is 0. So we took the 5 key points in step 2 and evaluated them in step 3. Step 4, you guys can probably do better than me, is draw a nice, smooth, continuous curve that connects to those 5 points. And then step 5, where necessary, that's where you extend the graph as needed, because you know it's going to continue on in a periodic fashion. So let's look at another example a little bit of how we can develop some different variations of the basic y equals sine graph. So in this example, y equals 1/2 sine x. Do you already have a suspicion what that graph might look like? So put that in your head, and then let's put it into our body here and see what we get. Step 1 is identify the amplitude. The amplitude is 1/2. Check. After that, we want to identify the period. Well, the period we have to remember of a sine graph is a full 2 pi. So the period would be 2 pi divided by 4 gives us pi halves. So that tells me then that there's a key point. One of the key x values occurs every pi halves along the graph. So the first point is 0. The next one is pi halves. Pi halves plus another pi halves is pi. Then 3 halves pi. And then 2 pi. So we're able to use the amplitude. Well, identify the amplitude. Use the period to help us determine where those 5 key points are at. Then from there, we're going to use those 5 key points to determine the values of this particular function. So the sine of 0, 1/2, the sine of 0 is 0. Sine of pi halves, and 1/2 of that, the sine of pi halves is 1. 1/2 of that would be a 1/2. The sine 1/2 sine of pi is 0. 1/2, the sine of 3/2 pi is negative 1/2. And then 1/2 sine of 2 pi. So I was able to use our function, or our graph, evaluated for y for every one of these key x value points. Then step 4, I'm going to draw a nice, smooth, continuous curve through those points. And now I graphed this graph over the period from 0 to 2 pi. And then if we need to extend, we may extend both directions as much as we feel that we need to do. So we've used our amplitude. Notice what this graph does too. We have an amplitude that was less than 1. Because if we remember the graph of the sine graph, was such so that the half of the amplitude, you see that every point along this graph is 1/2 the distance, or 1/2 closer to the x-axis. Let's look at another example. The task we're given on this one is to compare two different sine graphs together. Y equals sine of x, and then y equals negative 2 sine of x. And then after that, we want to graph the extension from negative pi to 3 pi. So let's begin with understanding again, remember what the graph of y equals sine of x equals. There's 5 key points along the graph along its period. And we've done this before, so you already know where those key points are at. Pi halves, pi, 3/2 pi, and so forth. And then the graph has a nice, smooth graph such as that. And then I think what we'll do is we'll go ahead and we know this is the point 0. This was pi halves. That's the point pi. 3/2 pi, and then 2 pi. We found those 5 points because we know the period is 2 pi long. Each key point happens at a quarter of the way along that period. So I divide 2 pi by 4. Got my period. All right, so that's the graph of y equals sine of x. And then ultimately I want to graph it from negative pi to 3 pi. So let's see if I can get my graph right here. As such. And 3 pi is going to come right back down on that x-axis. I guess I should have extended that out a little bit further. All right, so there's y equals sine of x graphed all the way through that point. Then what do we think y equals negative 2 sine of x will do? We've already identified the period and the chunk marks along the way. The negative 2 is the amplitude. So every single point along the graph, the amplitudes can be factored by a negative 2. So at 0, it will still be 0. At pi halves, sine is 1, but we're going to multiply it by a negative 2. So notice that it's going to kind of be inversed a little bit. And then I go through and follow that process all the way back down. And so forth. Whoops, I noticed that I did not graph that one correctly. It should have only gone up to here, folks. You noticed that, didn't you? Yeah. All right, so what the graph will look like then with a negative 2 amplitude. It has the same quality. It looks like a sine function. It's just inversed and stretched by a factor of 2. And then, of course, drawn it from pi, this is negative pi, all the way to 3 pi. So what we did here is we based the y equals sine graph. Off of that, we were able to graph negative 2 sine of x. we had a negative amplification that time.